For decades, the diesel engine was a joke on the railroads. Too powerful, too violent, it tore gearboxes apart like paper. Steam ruled the rails, and every expert agreed diesel would never work for locomotives. But a Swiss immigrant named Hermann Lemp saw what no one else could see. He didn't need stronger gears, he needed no gears at all. His solution was so simple, so elegant, that the railroad establishment laughed him out of the room. Until 1924, when his diesel locomotive outran every steam engine on Earth and changed transportation forever. The system they ignored had just made steam power obsolete. By the early 1900s, the railroad industry had a problem it couldn't ignore. Steam locomotives were dying, and everyone knew it. Steam had ruled the rails for nearly a century. Massive iron beasts hauled freight across continents, their pistons hammering like the heartbeat of industry. But the cracks were showing. The engines overheated in tunnels. They required armies of workers to shovel coal, haul water, and scrape ash. They wasted half their fuel just keeping the boiler hot overnight. Maintenance crews worked around the clock. For every hour a steam locomotive ran, it spent another hour in the shop. The answer seemed obvious. Diesel. Rudolf Diesel's engine was a marvel. More efficient, cleaner, and powerful enough to shame any steam engine. But there was a problem no one could solve. The diesel engine was too violent for the rails. And here's why. A diesel engine produces massive torque the instant it fires. When you try to connect that raw power directly to the wheels through mechanical gears, the way steam locomotives did, the transmission tears itself apart. The gears couldn't handle the shock. They shattered like glass. Engineers tried heavier gears, stronger metals, complex clutch systems. Nothing worked. Every diesel locomotive prototype ended the same way. Twisted drive shafts, exploded gearboxes, and engineers standing in the wreckage wondering what went wrong. In 1912, Rudolf Diesel himself came to America to prove his engine could power a locomotive. He built a massive 1,000 horsepower direct drive unit. The engine was perfect, but when they opened the throttle, the mechanical transmission lasted less than an hour before it ripped itself to pieces under the strain. Hermann Lemp was there. He watched it fail. Lemp was a Swiss immigrant who had arrived in America at 19, desperate to work for Thomas Edison. He got his wish, joining Edison's company and working on one of Edison's first electric locomotives. He'd even survived being thrown from that locomotive when Edison accidentally reversed it during a test. After Edison, Lemp moved to General Electric, where he became one of the company's most respected electrical engineers, a man colleagues compared to Steinmetz and Pupin. But Lemp saw something in that 1912 failure that no one else did. The problem wasn't the diesel engine, it was everything between the engine and the wheels. While every other engineer tried to build stronger gears, Lemp asked a different question. What if we didn't need gears at all? Lemp's solution was radical because it required thinking like an electrician, not a mechanic. Imagine you're trying to connect a fire hose to a water wheel. If you blast the wheel directly with full pressure, it explodes. But if you let the water flow into a reservoir first, then control how much spills onto the wheel, you can harness all that power smoothly. That's what Lemp realized. He didn't need to tame the diesel engine, he needed to convert its violence into something controllable. His answer? Electricity. Instead of connecting the diesel engine directly to the wheels through gears, Lemp proposed something no one had attempted at locomotive scale. The diesel engine would drive a generator. The generator would produce electricity. That electricity would flow to traction motors mounted on the wheels. The diesel engine would never touch the wheels at all. It was elegant, it was simple, and it solved the torque problem instantly. Electrical current doesn't shatter. It doesn't care how much power you throw at it. A generator can absorb any amount of mechanical force and convert it smoothly into electrical energy. The traction motors, in turn, could handle any load without braking. But Lemp saw a problem no one else had considered. How do you coordinate the engine and the generator? A diesel engine has a fuel governor that controls its speed. A generator has field excitation that controls its electrical output. If the two aren't perfectly synchronized, the system tears itself apart in a different way. Too much load on the generator and the engine stalls. Too little load and the engine over-revs and destroys itself. An operator would need two hands, two levers, two sets of gauges, one for the engine, one for the generator. It was a nightmare. Lemp spent months in General Electric's laboratory, filling notebooks with calculations. He studied how generators responded to load. He analysed how diesel engines behaved under varying fuel flow. He was searching for a way to make the two machines speak the same language. Then, in 1914, he found it. He designed a single control system that automatically linked the engine's fuel regulator to the generator's field excitation. One lever. When the operator pushed it forward, the system would simultaneously increase fuel to the engine and adjust the generator's output to match. The two machines would rise and fall together, perfectly balanced, like dancers moving in sync. It was the world's first coordinated diesel-electric control system. He filed a patent in June 1914, US patent number 1,589,182, the blueprint for every diesel-electric locomotive that would ever be built. But when Lemp presented his design to the railroad industry, they laughed him out of the room. Too complex, they said, too delicate, another thing to break. They wanted diesel to work like steam. Lemp had just proved it never would. But for nearly a decade, Lemp's patent sat in a filing cabinet at General Electric. The railroad industry wasn't interested. They had bigger problems, like winning a war. When Lemp filed his coordinated control system in June 1914, the world was weeks away from the First World War. By August, Europe was burning. America's factories shifted to war production. Diesel engines went into submarines and ships, not locomotives. General Electric's upper management shelved Lemp's design. It was brilliant, they admitted, but there was no market. Steam locomotives were good enough. Diesel was still a curiosity, an experiment for engineers with too much time on their hands. Lemp didn't argue. He simply kept refining the system. He improved the governor design. He calculated more precise ratios between engine speed and generator load. He filled notebooks with equations that proved his system could handle any condition. Cold starts, heavy grades, variable speeds. But without a locomotive to test it on, his work remained theoretical. Then, in 1923, something changed. Steam was collapsing under its own weight. Railroads were hemorrhaging money on maintenance. Boilers cracked. Fireboxes wore out. The coal strikes of the early 1920s had shown just how vulnerable steam power was to labour disputes. Railroad executives began asking a question they'd avoided for years. What if diesel actually worked? General Electric finally took the gamble. They approached Ingersoll Rand, who built rugged diesel engines, and the American Locomotive Company, who built the bodies. The three companies formed a partnership. Ingersoll Rand would supply the engine. Alco would build the frame and mechanical components. General Electric would install Lemp's electrical system and control apparatus. The target, a 300 horsepower box cab switching locomotive, small enough to be practical, powerful enough to prove the concept. Construction began in late 1923 at GE's Erie plant. Lemp supervised every detail. The diesel engine sat in the centre of the locomotive, bolted to a massive generator. Electrical cables ran to traction motors mounted on the wheel axles, and at the heart of it all, Lemp's control system. A single lever in the cab that governed both the engine's fuel flow and the generator's field excitation simultaneously. On paper, it was elegant. In metal, it looked like a mechanical Frankenstein. December 1923. The locomotive was complete. Lemp stood in the cold, Erie workshop as the engine coughed to life for the first time. The diesel rumbled, the generator hummed. He pushed the control lever forward. The engine's RPM climbed. The generator's output rose in perfect synchronization. The traction motors engaged. The 60-ton locomotive rolled forward smoothly, as if it had been doing this for years. No grinding gears, no violent shuddering, just smooth, continuous power. Lemp exhaled slowly. The system worked exactly as the mathematics had predicted. But GE's management wanted more than a successful test. They wanted proof that would convince the most skeptical railroad executives in America. So in June 1924, they released the demonstrator locomotive for a trial tour. 13 railroads, 13 months, every test they could imagine. The first railroad to receive it was the New York Central. They were brutal. On August 14th, 1924, NYC engineers hooked the little diesel to a train of 93 freight cars on level track. It was a test designed to humiliate. Steam switchers struggled with 40 cars. This diesel weighed half as much. Lemp watched from the platform as the engineer opened the throttle. The diesel engine climbed to full power. The generator fed current to the traction motors. The wheels bit the rails. And slowly, impossibly, all 93 cars began to move. The New York Central engineers stood in stunned silence. Over the next 13 months, the demonstrator traveled from railroad to railroad. The Baltimore and Ohio tested it in their yards. The Lehigh Valley ran it on mountain grades. The Jersey Central put it through switching operations in brutal winter cold. Every railroad subjected it to conditions that would cripple a steam engine. The diesel never failed. It didn't overheat. It didn't require water stops. It didn't need a fireman shoveling coal. One engineer could operate it with a single lever. When the day's work was done, the crew simply shut it down. No banking fires, no overnight maintenance. In the morning, it started with the push of a button. The numbers were undeniable. The diesel consumed half the fuel of a comparable steam engine. It required a fraction of the maintenance. It could run for days without stopping. By 1925, orders began trickling in. The first production diesel-electric locomotives rolled off the assembly line. 300 horsepower box cabs, built to Lemp's specifications. 6 went to New York railroads. 2 went to Chicago. The rest scattered across the country, quiet pioneers of a revolution no one had seen coming. The railroad establishment had ignored Lemp's system for a decade, but now, as his locomotives proved themselves in yard after yard, the truth became impossible to deny. Steam's reign was ending, and the weapon that would kill it was a Swiss immigrant's patent for a control system so simple it fit on a single lever. The diesel-electric locomotive didn't conquer the railroads overnight. It crept in quietly, one switching yard at a time, while steam engines still dominated the main lines. By 1930, only a few dozen diesel-electrics were in service across America. They were curiosities, expensive experiments that railroads bought to test, but didn't trust. Steam was familiar. Steam was proven. Diesel was the future, perhaps, but the future could wait. Then the Great Depression hit, and waiting became a luxury no railroad could afford. As traffic collapsed and revenues plummeted, railroads began calculating costs with brutal precision. A steam locomotive required constant maintenance, boiler washing, ash removal, water stops every 100 miles. A diesel-electric could run for days without servicing. Steam engines needed crews working around the clock to keep fires banked. Diesels started with the push of a button. The numbers were undeniable. Diesel-electric wasn't just better, it was cheaper. And in the Depression, cheaper meant survival. Orders accelerated. By the late 1930s, new companies like Electromotive Corporation were building entire fleets of diesel-electric locomotives, all using variations of Lemp's coordinated control system. His 1914 patent had become the foundation of an industry. Between 1925 and 1931, the GE Ingersoll-Rand ALCO partnership produced 50 locomotives built to standard designs, the first manufacture of diesel locomotives on a production basis. Then came World War II. The US Navy needed reliable diesel engines for ships and submarines. They poured research funding into diesel technology, advancing it by decades in just a few years. Meanwhile, the government ordered steam locomotive builders to focus on proven steam designs, giving diesel manufacturers like Electromotive a crucial advantage in development and production capacity. When the war ended in 1945, American railroads faced a crisis. Their steam fleets were worn out, overworked, and obsolete. They needed to rebuild. This time, they didn't choose steam. By 1950, diesel-electric locomotives outnumbered new steam production. By the early 1960s, the last mainline steam engines were being retired. The transformation was total. In less than 2 decades, steam power, which had ruled the rails for over a century, had vanished completely. Every diesel-electric locomotive that replaced them used Hermann Lemp's control principle, the one-lever system, the coordinated governor, the automatic synchronization between engine and generator. It had become so standard that most engineers didn't even know where it came from. Lemp continued working well into his later years. He became chief engineer of the locomotive department at Ingersoll Rand, applying his control system expertise to real-world locomotive production. In the late 1930s, he was even involved in railway construction for the 1939 to 1940 New York World's Fair. In 1951, the Franklin Institute awarded him the George R. Henderson Medal for his contributions to diesel locomotive technology, one of the highest honours in mechanical engineering. 3 years later, on March 31, 1954, Hermann Lemp died at his home in Ridgewood, New Jersey. He was 91 years old. By then, his control system had been in continuous use for 40 years. It would remain the standard for decades more. Today, if you hear a freight train rumbling through the night, you're hearing Hermann Lemp's legacy. Modern diesel-electric locomotives still use his fundamental principle: a diesel engine driving a generator, feeding traction motors, all coordinated by a single control system. The governors are now computerized. The calculations happen in microseconds instead of mechanical movements, but the logic is identical to what Lemp designed in 1914. His system didn't just power trains. It influenced marine propulsion, mining equipment, and heavy construction machinery. Anywhere raw power needed to be converted into controlled motion. The principle of electrical transmission, coordinated automatically, became one of the foundational concepts of modern engineering. Lemp never sought the spotlight. He simply solved the problem no one else could see. While every other engineer tried to force diesel into steam's mechanical paradigm, Lemp asked a different question. He thought like an electrician, not a mechanic. And that shift in perspective changed everything. The hidden system that made diesel electric possible wasn't just a machine. It was a way of thinking. A recognition that the solution to a mechanical problem might not be mechanical at all. That sometimes the best transmission is no transmission, just the smooth conversion of energy from one form to another. Hermann Lemp didn't just make diesel electric possible, he made steam power obsolete. And he did it with a control system so simple, so elegant, that it fit on a single lever. A hidden system, pushed by one man, resisted by institutions, that proved decisive under pressure. The railroads ignored it for a decade, but once they accepted it, they could never go back.